Okay, today we will talk about simple harmonic motion. We'll talk about the position, velocity, and acceleration functions for something undergoing simple harmonic motion. And just as a refresher, simple harmonic motion is some sort of motion that results from a restoring force that is proportional to the displacement of the object. So an example is a spring is a great example of that. Also a pendulum is a great example, and we'll go into more details about those at a later date. Cool. So we know that our general equation for something undergoing simple harmonic motion is either x of t, so position, is equal to a cosine omega t, or a sine omega t. Either of those would work. So let's go ahead and just define a couple things with that equation. So again, a is the amplitude. And again, the amplitude is the distance from equilibrium to the max or min point. Omega, that is called the angular frequency, or it is also called angular velocity. We'll see both of those things. And omega is equal to 2 pi over the period. And the period, again, is the time for one complete cycle or one revolution. So time for one cycle, or one revolution. Great. So we have our general function. X of t equals a cosine omega t. Let's go ahead and graph that. So if I look at this function, so I know it's a cosine function. And again, a sine omega t would be totally okay as well. Different situations will use different ones. So cosine function, I know that the max starts at t equals 0. If I plug in 0, cosine of 0 is 1, which is the maximum value of cosine. So we'll start at our amplitude a. So this is our max point. Our min point is going to be negative a. So we'll start at a. We'll go down to equilibrium. Then at half a cycle, we'll be back at negative amplitude, and then we'll be back at equilibrium again, and then after one complete cycle, we'll be back to where we started. So let's go ahead and graph this cosine function. So it's something like this. Awesome, cool. And so keep in mind, at x equals 0, or sorry, excuse me, time t equals 0, time half a period, and a full period, it looks like we are at our max or min amplitudes. So that is going to be the turning point of the function, which is when your velocity is going to be 0. So in just a second, we're going to talk about the velocity function. So if you have velocity, how do you find, or if you have position, how do you find velocity? Well, we take the derivative. Let's look at this position function. So at those points we just talked about, if we were to take the derivative at those points, what is our velocity? Oh, cool. Our velocity would just be 0 at all those points. And again, that is the derivative. So velocity is 0. So that's going to be dx dt equals velocity. So at that point, each of those points, the velocity is 0. Cool. So now let's go ahead and graph our velocity function. So I'm going to scroll down. Let's see. Perfect. So again, we said that velocity is going to be the derivative of position with respect to time. So anytime we have something that is a not constant function, we need to take the derivative with respect to time. So our position function that we chose was a cosine of omega t. So looking at this function, we know t changes. That's a variable. So t is a variable. A is the amplitude. The amplitude always stays the same. And omega is the angular frequency or angular velocity, which always stays the same as well. So A and omega are going to be constant. So that'll just help remind me when I take the derivative. So, okay, take the derivative. Derivative of, so we'll just pull out A is just a constant. So d dt of cosine omega t. So the derivative of cosine is negative sine. So that's going to be negative sine of omega t. But now we need to use our calculus chain rule idea and take the derivative of the inside. So the derivative of omega t is just omega. So I'll put that there. So if we go ahead and just rewrite this function, that's just going to be negative a omega sine of omega t. So in this situation, this is going to be our velocity function. So v of t equals negative a omega sine of omega t. So if we look at this velocity function, the minimum value it'll be will just be its amplitude, which is negative a omega. So this is like the amplitude of the function of v of t function. While the maximum value this could be is just a omega. Cool. So let's go ahead and graph that. So we know at t equals 0, sine is going to be 0. So we'll put that in there, and that'll occur also at t over 2, and period. So we have a negative in our velocity function. So we're going to go down to start. So it'll be negative omega will be our amplitude, and a omega amplitude. And I guess I should say our amplitude is a omega. Negative a omega is the min velocity. Cool. So let's go ahead and graph that. So we'll have this, and we will graph this velocity function away. Awesome. Cool. And I would encourage you is to redraw on your own piece of paper your position and velocity functions, and just confirm that if you go from your position graph, taking a derivative, to your velocity graph, that your maxes and mins make sense and that they correlate. Cool. So we are going to go ahead and go on to our acceleration function. Great. So for velocity, we took the derivative of position with respect to time to get velocity. Now for acceleration, we will take the derivative of velocity with respect to time. So dv dt. So you have d dt, and again, our velocity function is negative a omega sine of omega t. Great. So let's take the derivative. So negative omega, this will just stay, nothing changes about those. Derivative of sine of omega t, that's going to be cosine of omega t. Now we need to do the chain rule. So the derivative of omega t, that is just going to be omega. So if I simplify our function, it is going to be negative a omega squared cosine of omega t. So let's just rewrite that. So a of t is going to be negative a omega squared cosine of omega t. Oops, excuse me. Sorry about that. Cool. So that is our acceleration function. Great. So again, for this, like our amplitude is going to be a omega squared. So that is just whatever is in front of the function. Our min value of acceleration is going to be negative a omega squared. So let's go ahead and graph this. So at t equals 0, cosine is going to be 1. So if we plug in that, then that'll be a omega squared. So we're going to start down here for cosine right here. Cool. Then we'll go here. Then at half a cycle, we'll be at a omega squared. We're back to 0. And then at one full cycle, we'll back to where we started. Let's go ahead and graph this cosine function. Great. Here's how we pause this. Oh, can't figure out the pause. Sorry about that.